Okay, we are looking at optimization scenarios, which involve finding maximum or minimum values. Number one, a printer needs to make a poster that will have a total area of 200 inches squared and will have 1-inch margins on the sides, a 2-inch margin on the top, and a 1.5-inch margin on the bottom. What dimensions will give the largest printed area? Seeing the word largest right here indicates that it's optimization. There are many different areas that the printed part could have, but we are looking for the largest. One thing that you should do first is draw this. An image will help you figure out what equations to use, what relationships to set up. So this could be our poster, and now we have a printed area and we have margins. The margins are empty space, and the printed area is some rectangular region inside all of that. There are 1-inch margins on the sides. These markings show that, and I could maybe make a dashed line to show that I cannot cross that line with any printed text or anything printed. Now there are margins on the top and the bottom. On the top there's a 2-inch margin, so we'll extend this dashed line and mark that that's 2 inches. And on the bottom, it's 1.5 inches that we're going to space out away from the bottom of the poster. The printed area is this interior rectangle. What dimensions will give the largest printed area is what we're trying to find, and we already know the size of the poster. The poster has a total area of 200 inches squared. It's a rectangular poster. We don't want to assume it's a square. So we need to label these dimensions. Let's call the length of the bottom x, and then we'll look at the length of the height as y. And now we can state one relationship. X times y equals 200. What's another relationship that we can find between these values and numbers? That would be the printed area. The printed area is also a rectangle, and we want to maximize its area. How do we find its area? Well, same as you find the area of the overall poster. It's the base times the height. The base is this red line that I'm drawing right now, and the height is this other red line that I'm drawing. Let's figure out how long those are. If we have already labeled x as the entire base length of the poster, then we can use this one, which is the distance from here to here, and this one, the distance from here to here, to find the length of this red line. This red line is x minus 1 minus 1. That would be x minus 2. And then the height would be done the same way, except we have different margins that we're subtracting. The entire height of the poster is y. This red line has a length that is y minus 2 minus 1.5. Minus 2 and then minus 1.5 would be minus 3.5. So that's y minus 3.5. Now we can state the area of the printed region. It is the base, x minus 2, times the height, y minus 3.5. Equation number 2 has 3 variables in it, a, x, and y. Equation number 1 has 2 variables, x and y. We have a system of equations at this point, and we're trying to find the largest area of this red equation. So that means the red equation has some sort of curvature to it, and we are looking for when that curvature reaches a highest point or a lowest point. And we can do that by finding the derivative of the equation and setting the derivative equal to 0, and then determining if those critical points where the derivative equals 0 represent minimum or maximum points. Before we can find the derivative of this equation, it will be helpful if we take this equation and use substitution to change this equation and reduce it from 3 variables down to 2 variables. So let's take the blue equation and isolate one variable. I'll isolate y. Divide both sides by x. Y equals 200 divided by x. Now I can take that expression and replace y with that expression in the red equation. a equals x minus 2 times 200 over x minus 3.5. We've now converted the red equation into a two-variable equation. We have the area is dependent on x. Before we find the derivative of this area function, let's simplify it to make it easier to find the derivative. It's a binomial times a binomial, so I'm going to distribute these expressions to remove the parentheses. After this step, I can combine like terms. The 200 and the 7 can be combined to make 207, and then the rest I can just bring down. Now I know I'm about to take the derivative of this, so I'm going to write 400 over x as 400x to the negative 1 to make it easier to find the derivative of the expression 400 over x. A prime equals 207 becomes 0, it's a constant, minus 3.5 plus 400 x to the negative second power. Now I want to set my derivative equal to 0. A prime equals 0. Negative 3.5 plus 400 over x squared equals 0. I can add 3.5 to both sides. 400 over x squared equals 3.5. I can multiply both sides by x squared. 400 equals 3.5x squared. Now I need some more space, so I'll go over to here. I can divide both sides by 3.5, and I'll round this to 2 decimal places. 400 divided by 3.5 is approximately 114.29. That's equal to x squared. So we'll find the square root of that expression. That would be plus or minus approximately 10.7. But we would not have a negative value for x, because then that would not be a poster. We couldn't make a poster with negative dimensions. So we'll say x is approximately 10.7. We're trying to find the dimensions of the poster. So we have one of them. Now we just have to find the other one. We can go up to equation number 1 here, which is already solved for y. Y is isolated right here. So y is 200 over x. So 200 over 10.7. That's approximately 18.7. So the dimensions for this poster will be approximately 10.7 inches by 18.7 inches. And one way to see if your work matches up with a visualization of this function is to take the area function in its simplified form, which would be right here, and input that function into Desmos using a y right here and an x here and here, and then look at the curvature of it and see if the maximum area, a relative maximum of this function, occurs at an x value of 10.7. Not a y value, an x value, because this equation has a dependent on x. That would be a nice thing to do right now if you would like to see what this looks like from a graphical perspective. Number 2, a tank with a rectangular base and rectangular sides is open at the top. It is to be constructed so that its width is 4 meters and its volume is 36 cubic meters. If building the tank costs $10 per square meter for the base and $5 per square meter for the sides, what is the cost of the least expensive tank and what are its dimensions? Let's start by drawing a picture of this tank. It has a rectangular base and rectangular sides. I'll draw a rectangular side and then try to draw the rest of the tank from there using a little bit of a perspective drawing. So inside here, I'll draw dashed lines because we can't see those, and then dashed line for that. We know the width is 4 meters, so I'll put 4 meters right there. I do not know this other dimension, the length, maybe you'd call it, I'll call it x, and I don't know the height, I'll use a y, but I do know the volume, and the volume is length times width times height. In this case, that would be 4 times x times y. This looks like a 3-variable equation, except we are given the volume. It's 36 cubic meters, so I can replace v with 36. 36 equals 4xy. That's equation number 1. Equation number 2 would be the cost equation. We want the cost to be the least expensive cost possible. The cost is based on the material used to build this tank, and the sides of the tank are all rectangles. So I'm going to write down the different rectangles, and we'll talk about the cost of each of those rectangles. One of the rectangles has a base of x and a height of y, and there are 2 of them. So the cost is going to be 2xy, and then the sides are $5 per square meter. So I'm going to multiply that by 5. That would be 10xy. I'll call that side number 1. Side number 2 is a rectangle that is 4 along the base and y along the height, and there are 2 of them. So the cost of those would be 2 times 4 times y. That's the area of both of them added together. And then I'm going to multiply it by the cost per square meter of the sides, which is again 5. So 2 times 4 is 8. 8 times 5 is 40. 40y is the total cost of those 2 sides. And then lastly, we have the base. The base is a rectangle that is x by 4, and there's only one. So the cost is 4x multiplied by the price per square meter, which is 10. So that's 40x. Now I can go up here and make my second equation. The cost of building this thing is all of these parts added together. 10xy plus 40y plus 40x. This cost equation has 3 variables, c, x, and y. But this equation in blue has 2 variables, so we can isolate one of the variables. I will solve for y. So y equals 9 over x. Now I can go into the cost equation and replace y with 9 over x. Now I'll simplify the equation as much as I can, and you'll notice one of the terms is 360 over x. So before I take the derivative, I'm going to write that as an expression with a negative exponent, 360x to the negative first. Now I can take the derivative in that form. C prime equals 0 minus 360x to the negative second plus 40. And I'll set the derivative equal to 0. I'll write negative 360x to the negative second as negative 360 over x squared plus 40 equals 0. I can move the 40 to the other side of the equation. I can multiply both sides by x squared. I'm going to divide both sides by negative 40 to get 9 equals x squared. If you take the square root of both sides, x equals plus or minus 3, but we would not include the negative value because this represents the dimensions of a box, or the side lengths of a box. And so we'll just take x equals 3, and then we can solve for y using the blue equation right here. Y equals 9 over x. So y equals 9 over 3. Y is also equal to 3. And we already know the width is 4. So now we know our dimensions. We're supposed to find the dimensions of the container. So that would be 3 by 3 by 4, and that's in meters. And then we want to find the minimum cost. To find the minimum cost, we can actually just use the x value because our cost equation right here is in terms of x. So replace these x values with 3, or go up here and replace these x values with 3. 360 over 3 is 120. 90 plus 120 is 210. Put a 3 right there. 40 times 3 is 120. 210 plus 120 is $330. You could also use a calculator to help you find that.